let f r to r be given by, you see that piecewise definitions of the function is given. X less than 0, 1/5 degree polynomial. Between 0 to 1, quadratic polynomial. Between 1 to 3, a cubic polynomial. And more than equal to 3, we have a combination of multiplication of x with log x and a linear function. So now the question says that f is increasing on minus infinity to 0. F dash has a local maxima at x equal to 1. F is onto and f dash is not differentiable at x equal to 1. So first of all, if we quickly see the option f is onto or into. Okay, so for that, let me start by checking the rough nature of the graph. Okay, so let us do one thing. Let us start with the first piece. You see, is the 5th degree polynomial. So from where the graph is going to start? It will of course start from minus infinity, x equal to minus infinity. If we substitute minus infinity here in the first one, of course it will tend to minus infinity power 5. So overall the value will tend to minus infinity, because compared to this term, these terms will be negligible at minus infinity. So the function is tending to minus infinity at minus infinity. So suppose we are just for a dummy point, I am writing minus infinity comma minus infinity. Of course there cannot exist such point, but just for analysis purpose I am writing. And at 0, what is the limiting tendency? If we put 0 here, it is tending to 1. So 0 comma 1, it is tending to 1. Okay, next 0 to 1, next 0 here, substituting 0, you are getting 1. So the graph will start from here only for the second piece, and 1 substituting, you will get 1 minus 1 plus 1, that is 1. So between 0 to 1, I am expecting a graph say something like this, and here suppose I am expecting a graph say something like this. I am not drawing the exact graph. My intention is to just see the nature of the graph. Nature of the graph is from where the graph is starting, from where the graph is ending. You see, we know that the graph starts at minus infinity and it is ending at plus 1, and we know that it is a polynomial, so it must be continuous. So I am just drawing a rough sketch of a continuous graph. I am not drawing the exact graph. Okay. Next, it is starting, this one is started from 0 comma 1 and ended at 1 comma 1. Ended at 1 comma 1. So this is like, this is a parabola, upward opening parabola. Next one is 1 to 3. We have a cubic polynomial. 1 substituting here, if you substitute 1, you will get 2 by 3 plus minus 8 by 3, that is minus 2 plus 7 minus 4. So it will be 1. So again the next graph will start from here, 1 comma 1, and 3 substituting here. If you substitute 3 here, it will be 2 by 3 into 27 minus 4 into 9 plus 21 minus 8 by 3. So this will be 18 minus 36 plus 21 minus 15 minus 8 by 3. That is 1 by 3. So it will end at 3 comma 1 by 3. Suppose 3 comma 1 by 3 is here. And again it is a continuous graph. So I am just joining the dots by a continuous rough sketch. And finally, when x is greater than or equal to 3, here if you substitute 3, if we put x equal to 3 here substituting x equal to 3, you will get 1 into ln 1 minus 3 plus 10 by 3. ln 1 is 0, so this is again 1 by 3. That means the next piece again will start from 1 by 3 only. The next one will start from here, and as x tends to plus infinity, this one is tending to, as x tends to plus infinity, this is tending to plus infinity into log of infinity, that is also infinity. Infinity into infinity, infinity of second degree minus infinity, that is infinity of first degree. So compared to this term, x is negligible, right? So ultimately the function is tending to plus infinity. So from here, it is a continuous function that is going to plus infinity, right? This is a continuous function. Of course, there is no discontinuity for x greater than or equal to 3. So the graph will start from here and it will go up to say plus infinity. So I am again writing a hypothetical point plus infinity comma plus infinity. So clearly you can see that the graph is starting from minus infinity and continuously taking all the values and going up to plus infinity. So we are confirmed that f must be an onto function, because the range of the function must be minus infinity to plus infinity, which is equal to the codomain of the function, right? Codomain is equal to the range. That means function must be onto. So that part is clear. So we are confirmed that the function is onto and it is a continuous function. There is no jump or any discontinuity in the graph. The function is starting from here and it is taking all the value and going way up to plus infinity. So there is no discontinuity in the graph of the function. Now next we'll come to the further analysis of the remaining options. So remaining options, if you verify, we know function is continuous. So next option we can verify is f is increasing on minus infinity to 0. So let us take minus infinity to 0 this piece and go for the derivative of the function. F dash x is equal to 5x to the power 4 plus 20x cube plus 30x square plus 3. This is the 30x square plus 20x plus 3. 20x plus 3. This is the derivative of the function. Now we need to verify f is increasing or not. That means can this derivative is always non-negative or not. So if I take 5 common from the first 4 terms, it will be x to the power 4 plus 4x cube plus 6x square plus 4x. So you can see this is a binomial expansion. So adding 1 and subtracting 1. I have added 1 here, 5 into 1, balanced here minus 5, right? Now you see that this is an interesting binomial expansion. This is actually the expansion of x plus 1 to the power 4 minus 2. Okay, because this 4 is actually 4c1, this 6 is 4c2, this 4 is 4c3. So this is a binomial expansion of x plus 1 to the power 4. So the function, the derivative is 5 into x plus 1 to the power 4 minus 2. Okay, now is the derivative is always positive? That we need to verify. You can see that derivative value at minus 1, if I substitute x equal to minus 1, this is becoming 0. So 0 minus 2, that is a negative value. But if we substitute say x equal to, our domain is 0. So if we substitute say x equal to minus 2, it will be 5 minus 2, that will be positive. So that means the derivative value is changing sign. Somewhere the derivative is positive, somewhere the derivative is negative. That means I cannot say that function is increasing on minus infinity to 0 because there are some x value for which the derivative can be negative also, right? We need to verify is option B, f dash has a local maxima at x equal to 1 and f dash is not differentiable at x equal to 1. So these two are connected options. So we need to analyze the derivative and derivative in the neighborhood of x equal to 1. So let's see in the neighborhood of x equal to 1, that is we will take these two cases. So if I go for the derivative, it will be f dash x is when x is less than 1, between 0 to 1 the derivative is 2x minus 1. This is from 0 to 1 and from 1 to 3 the derivative will be, if I differentiate this function, it is going to be 2x square minus 8x plus 7. This is going to be the first derivative. Now the question is option B, that is f dash is not differentiable at x equal to 1. Okay, that is option D. So for that let us go for the double derivative f double dash x. F double dash x is equal to, first of all let us ensure continuity of the derivative. Is the derivative continuous at x equal to 1? So f dash 1 minus, to the left of 1 the tendency is 2 into 1 minus 1, that is 1, and the derivative for 1 plus, right tendency at 1 will be, we will substitute here, that is 2 minus 8 plus 7, that is also 1. So we have proved that the derivative is continuous at x equal to 1. So now let us go for the differentiability at x equal to 1. So let us go for the double derivative. So f double dash x is equal to, the derivative of this function is 2 when x lies between 0 to 1, and for this function the derivative is 4x minus 8, that is from 1 to 3. Now for the double derivative, if you check the limiting value, that is f double dash 1 minus, to the left the limiting value is 2, and f double dash 1 plus, the right tendency will be, we will substitute 1 here, so it will be 4 minus 8 equal to minus 4. So since the double derivative limiting tendencies are not equal, so we can say that the double derivative is not continuous. So in this case the single derivative is not differentiable. So option D is correct. And option B is f dash has a local maximum at x equal to 1. For local maximum for a continuous function at a point, we need to see that the derivative changes sign from positive to negative. We have checked that derivative is a continuous function. So derivative will have a maxima at x equal to 1 if the derivative of derivative changes sign from positive to negative. And that is what is happening. You see that left tendency, this is a positive value. This is the left tendency positive and the right tendency is negative. So derivative of the derivative is changing sign from positive to negative. That means we can definitely say x equal to 1 is a local maxima for f dash x. For f dash x. That is correct because derivative is changing from positive to negative. So option B is correct.